Yeah, the volume is maximum now. So let's start today's video. Hello everyone. I am going to discuss this lead code problem named this is sliding window maximum problem, lead code 239 hard problem. So without wasting much time, let's get started. So in this problem, we are given an array nums and there is a sliding window of size k which is moving from very left to very right, okay, and you can see the k numbers in the window, okay. Basically the window size is fixed, which is k, okay, and each time the sliding window moves right by one position, okay, return the maximum sliding window. Basically it's asking me to return a vector of integer which stores the maximum element of each window, right? So let's take this example test case. So in this test case, we are given this array 1, 3, minus 1, minus 3, 5, 3, 6, and 7, and here k is equals to 3, the window size. So let's now analyze all these windows. So the first window is this, in which the maximum element is 3, and the second window is this from index 1 to 3, and the maximum element is still 3. The third window is from index 2 to 4, and in this window the maximum element is 5, okay, and next window is from index 3 to 5, and in this window the maximum element is still 5. Now let's go to the next window. In this window the maximum element is 6, and in the next window the maximum element is 7, okay. So let's first of all write some observations. So the first window is starting from the index 0, whereas the last window is starting from index n minus k and going till index n minus 1, right? So, and the constraints for this problem is, and let n be the size of this array, and it's going up till 10 to the power 5, and the values of array nums, it is basically its absolute value is less than or equals to 10 to the power 4, okay, and k is also going till 10 to the power 5. Okay, so let's go to the brute force approach. You can easily see that in brute force approach we will go to each window and I will iterate to each element to find the maximum of that window, and you can easily see that this approach will take me big of n times k time complexity, which will go up till 10 to the power 10, which will give me TLE, because for each window, I have to iterate for each element and update the maximum element. And after completion of this window evaluation, I have to update the value in answer vector, that the maximum element in this window is 3, in this window is also 3, in this window it's 5, in this window it's also 5, and in this window it's 6, and in the last window it's 7. Okay, so this will take me big of n times k time complexity, which will definitely give me TLE. So let's now try to optimize my algorithm. So what we can do, uh, let's say if I am able to optimize the iteration part, the evaluation of maximum element of the window to big of 1 or big of log k something, I can optimize the solution, right? Let's say if I use a set data structure to store the current elements. Basically, to optimize the algorithm, I can do some kind of pre-computations where, let's say I am using a max type of set where the front element of the set is the maximum element, and I will make sure that the at every instance the size of set is less than equals to k, the window size, right? So let's now uh, see what can be the possible algorithm for using set. Let's say whenever a new element come and I insert it inside set, okay, And also I have to check whether the window size is greater than k or not. Let's say if the window size is exceeding k, I have to remove the front element. The Let's say if this is the array and currently my window is like this and its size is k plus 1. So in that scenario I have to remove this element so that my current window will be of size k, right? So insertion part will be of log k because the size of set will be k. So insertion operation will be of big of log k cost. And when I have to remove the front element, that I minus kth element, it will also take me big of log k time complexity. Also, whenever my index is greater than or equal to k minus 1, that is I am considering a window, because let's see this example. Yeah, whenever my index is greater than or equal to this particular index, I have a particular window. Let's say I am at this index, I have this window. When I am at this index, I have this window. When I am at this index, I have this window, and so on, right? But if I am at this index, I'm not having any window because the window size should be exactly k, but this size is less than k, right? So for valid window, my index should be greater than or equal to k minus 1, right? So yeah, whenever whenever the index is greater than or equal to k minus 1, that means I'm having a valid window and I have to include the maximum of that particular window inside the answer vector, right? And I am again using max type of set. So set the beginning element of the set will give me the maximum element of that window, which will cost me big of 1. So overall, if I say the overall time complexity for this algorithm, it will be big of n log k, right? And the space complexity will be big of k because I am considering a set of size k, at most k, right? But the constraints for this problem are up till 10 to the power 5, n is also 10 to the power 5, and k is also up till 10 to the power 5. If I use this approach, n log k approach, this can pass the constraints, and this can also be the valid answer for solution for this problem. But let's now try to optimize this solution to big of. I have already optimized the solution to big of n log k. Let's now try if I am able to optimize this solution to big of n only. If it is possible, then it will be the best solution. So let's now analyze some test cases. Let's say I am having this test case, right? I am having this array and 3 minus 1 minus 3 5 3 6 and 7. Okay, so let's now consider I am iterating from left to right in this array and considering each element one by one. Okay, so let's say initially I am at index 0. When I am at this index, I have basically a window of size k, right? So initially when I am at this index, I have inserted 1 inside my window, right? Now when I go to this index 1, the value at index 1 is 3, right? But 3 is greater than 1. When I am at this index, the window will be something like this, 1 and 3. But let's now analyze whether this currently the maximum value in this window is 3, right? Let's now analyze whether this 1 can affect the answers for upcoming windows or not. Because 1 is less than 3 and it is lying on left side of 3. And you can see that window is every window is like this. Initial window is this, then the next window is this. Basically the windows are traveling from left to right. So every time my window is going like is traveling by 1 unit, it is considering new element which is present at right. Yes, and removing the left one element. That means the leftmost element, which is not the maximum element, can't affect my answer for any upcoming window. That means this one is not useful for me at all, right? So basically that means I can remove this one. let's say I am getting one. I am having this element three as three at particular index one, and previously I was having one. Three is greater than one, so I can remove this one from this the particular data structure, right? And currently, when I am at this index three, index one, I am having three inside this data structure. Let's consider when I am at this particular index two. So now I am having minus one. So the current window is 1, 3, minus 1, right? So window size is k. So the window is completed now. Let's now, I have already removed 1 from this ds, right? Now let's see whether I can remove this minus 1 or not, because this is not a maximum value in this window. But as we already discussed that windows will propagate from left to right by 1 units, and every instance at every instance these will that window will include the next element and removing the previous one, right? So let's take an example like this, 1 3 minus 1 minus 2 minus 3, right? Okay, so the first window is this where the maximum element is 3, right? And let's now talk about the next window. Next window will be something like this, 3 minus 1 and minus 2. Again 3 is the maximum value, but in the next window will be minus 1, minus 2 and minus 3, where minus 1 will be the maximum value. So I can't remove this minus 1 from this ds, right? So at particular instance when I am at this index 2, I have completed my window of size 3, right? And the current ds is this. And again, the maximum value for this window is 3, which is present at front element of this ds, right? So I can directly see that there is some relation over here. So let's now try to make a algorithm for this thing. So I am basically iterating from left to right inside an array. Okay, and I'm considering a ds data structure. I I will decide it later on that I have to use which data structure, but uh, for time being, let's take a general data structure where I am storing some window elements, right? Initially, uh, let's say when it is empty, I am considering particular element to this. I am basically pushing element from this side to this, and for next value, I will compare this value with this particular value if the current value is greater than let's say if this is less than the previous value, I have to push this particular value at the back of this data structure. Let's take this example again. Yeah. Okay. So initially when I was at this index, I am considering one. Yes. Now when I reached one index one, I got three, but three is greater than one, so I have to pop this one. So when I am at this index, the ds will contain only three. Okay. When uh, I reach this index two, the ds will contain 3 and minus 1. Why? Because this minus 1 is first of all, this minus 1 is less than 3 and it is at right of 3. So I have to consider this element. I can't remove this. Okay. So when I reach this index, first of all, my first window has completed. So the maximum element is this, which is present at front. So I can store this answer as 3, right? Let's now consider when I am at this index. When I am at this index, I got minus 3. So minus 3 is greater than less than minus 3, minus 1. Minus 3 is less than minus 1. So I have to push this up. So I have pushed this minus 3 over here. But there is a thing. When I reach this index, I can see the data structure is also containing 3. And 3 is, yeah. 3 is there. So the new basically the new window has been completed. So in this window again the 3 is the maximum element, which is also already present at front. When I go to this index, I got 5. 5 is greater than minus 3, so pop this. 5 is again greater than minus 1, pop this. 5 is again greater than 3, pop this. So when I'm at this index 4, the DS will look like something, it will only contain 5, right? And again, this window has been completed. So for this window, the answer will be 5 because it's the only element which is present at front of this data structure, right? So let's now go to this element. 3. 3 is less than 5, so I have to push this. Okay. Yep. And again, this window has been completed. So again, this for this window only. For this window also, the front element is 5, so push this element to the answer vector. When I go to this index 6, this window has been completed. So push 6 is greater than 3. So pop this. 6 is greater than 5 also. Pop this. So for this index, the DS will look like this. And again, the only element present at the front of this DS is 6. So push this. Right. Now I am at this index 7. So 7 is again greater than 6. Pop this and push 7 again. When I am at this index 7, 7, this window has been completed. So for this window, the maximum element is this 7. Now, the first key observation which we can observe here is every time when I push an element inside this DS, there is a condition which is holding. If the current element array of I, it is less than the last element present in DS, then I push this directly, right? Else I pop I do pop operation or deletion operation in this DS until the last element is uh, becoming greater than this array element or it become empty, right? So this is the case. Again, so for this kind of a algorithm, we can see two, three things. Firstly, we are doing these type of operation. Whenever I am getting a greater element, basically there is a element which is present earlier and I got a new element ARR of I, the current element, which is greater than this element, right? So I have to remove this. Second type of operation which I am doing is pushing at back, right? So basically I am doing popping at front and pushing at back. Also, you can now let's try to like figure out which DS will be suitable for this kind of operation. If you know, we are having a data structure called Deque, which is double-ended queue, right? The double-ended queue supports both operations, pushing and popping at front and also at back. The popping at front, pushing at front, popping at back and pushing at back. All these operations, this particular DS DQ supports at cost big of 1 for all these operations. If I am able to do so, you can see that every time I am pushing an element to this DQ, it is the lower element. Basically, you can see every time the current position or the current picture of this DS is, it's a decreasing or non-increasing manner, right? So you can see that the pattern over here is basically it is containing elements in decreasing element, right? Decreasing order, right? So the maximum of this window is always is always present at the front element. So we can access the maximum of the window in big O of 1 time complexity just by accessing the front element by doing dq dot front, right? So let's now analyze the time complexity for this particular algorithm. In this algorithm, I am iterating from left to right for each element, and I am doing some kind of pushing, popping, and accessing the maximum element. Everything is going in big of 1, and I am iterating for each element. So basically, for each valid I, the all operations are of big of 1. So the overall time complexity over here is big of n. And if I uh, say the overall space complexity for this problem is big of k, because I am using doubly ended queue of size k at most, right? So let's now consider the uh, before going to the coding part, let's now discuss what will be the pattern that I will store in Deque. I will not store the elements in this Deque. I will store the index. If you want, I guess you can store elements also. But currently I am doing, I will store the indexes in this Deque, right? Let's go to the coding part now. So I am having this nums array and I am having this k, the window size. Let's now first of all create the vector in which I will store the answer. Okay, and also create a Deque double-ended queue, Deque, right? Deque. Okay, let's now first of all store the size of this array inside this n. Let's now iterate from left to right, I equals to 0 to I equals to n minus 1. Okay, so initially, let's say I am having the current element as nums of I. If this nums of I is greater than the last element present at the Deque, I have to do some popping operation. So while not of Deque is empty and Deque dot back, as I am storing the indexes over here, so I have to, for accessing the element, I have to do this nums of Deque dot back. If this is greater than the current element, I have to do some pop operations, pop from backside. So Deque dot pop back, right? And yeah, after doing the pop operation, either it is empty or it is not empty, I have to push back the current index. So Deque dot push back current index I, yes. And also I have to make sure if the Deque dot front is I minus k. Why I am considering this case? Let's consider. Let's say I am having this kind of Deque where it is considering at particular instance it is considering, let's say, 3 1 2, not like 1 0 minus 1, and yeah, in array basically I was having some kind of array where 3 1 0 minus 1 and something, and I was considering k equals to 3 sized window. So I am at currently I am at this index, right? So this element should not be the part of this window. So I have to check whether this I minus k is present in the uh, Deque. If it is present, I have to remove that, right? Because window size should not be exceeding k. So I have to check this using the if statement. If Deque dot front is I minus k, then I have to pop from front, Deque dot pop front, right? Otherwise, now when should I consider the like calculation of maximum element of that particular window? I have discussed that thing. Whenever my current index is greater than or equal to k minus 1, yeah, whenever my current index is greater than or equal to k minus 1, I have to consider all these like this, again this. When I am at this, I have to consider this window. Basically, whenever my current index is greater than or equal to k minus 1, that means I am having a valid window, and I have to include the maximum element of that window inside my answer vector. So answer dot push back dq dot front, because my dq is showing a monotonic nature in decreasing order. That means the front element of this dq is having the maximum element of that particular window. So that's why I am pushing this dq dot front, not dq dot front. It should be nums of dq dot front, because dq dot front is index. To access the element, I have to do this nums of dq dot front, and after doing so, I just have to return the answer vector. So let's now check this test case. This, there is some mistake, I guess, here. Let me check what's mistake is happening. I have initialized the vector. Okay, dq, right? Okay, okay. If, oh, this should be this. The current, if the current element is greater than the last element present in dq, then only I have to pop back. Yeah, is this matching with the output? 3 3 5 5 6 7, right? Let me try another test case also. 1 and 1. Okay, so 1 1 1. So for this test case should be, is it matching? Yeah, it's matching. So let's now submit this code. Check it is, whether it is passing sample tests or not. So sample test cases are passing. Let's submit the code. Yeah, it got accepted. So I guess you all understood the solution. This was the, this was all about today's video. So thanks for watching.